교수님 따라다니고 있습니다.
네네, 알겠습니다.
그렇군요. 네.
네, 그럼 시작을 할게요. So I apologize for the delay. Let me introduce the speaker very quickly and then we'll get started. I used to, when Kyunghyun gave a talk at our colloquium last semester, I gave a long, not long, but I gave a pretty long introduction with slides and everything, but I won't do that today because I think we like to just give him time to give his talk. But Kyunghyun is an alum, so he was here in computer science at KAIST, graduated in 2009, and did his PhD in Finland and postdoc at Milan and Montreal, and now he is at New York University where he's a SIGBAR fellow, and he's also a scientific director or senior director at Genentech, looking at drug discovery. So that's also very exciting. But today I think we're going to hear from him mostly about NLP, so data augmentation for natural language processing. So without further ado, let's give him a round of applause.
Well, thank you for the very generous introduction, and thank you for the applause as well. But yeah, so yes, Alex just introduced me. So these days splitting my time between your university and Genentech. Today, I'm going to stick to what I've done. I've been working on recently at New York University, but if you have any questions about what I do at Genentech about drug discovery as well as the antibody therapeutics, always feel free to reach out to me. And my email is really straightforward. My first name, last name at NYU.edu. Anyhow, okay, so before we start, let's talk about what we often refer to as manifold assumption. And this is, in some sense, the intuition and science behind data augmentation. But I call it data augmentation, but this is the assumption that is behind the success of any kind of machine learning algorithms that you can imagine. And the manifold assumption stated by Shofel, Shokov and Zien from 2006 states that the high dimensional data lie roughly on a low dimensional manifold. And what it says is that even though the data that we handle or that we work with tends to be in a very high dimensional space, or equivalent in a space whose volume is just gigantic. But in reality, the real data or the real data points that we observe or that we are interested in often lie in a very low dimensional subspace. And so some of the easy ways in which we can imagine is that most of the images, for instance, we can see, often you can apply only a small number of potential transformations without altering the actual content of an image. But then the number of the transformations that you can apply is really small. It's never going to be as high as, let's say, million dimensions or the millions of them. On the other hand, the images that we see, or at least when we represent it as a pixelated images, they do tend to be a single point in millions, if not billions of dimensional space. And in fact, this is not the kind of new thing. Everyone has been using this in some sense, in one sense or another, in order to build a very efficient, let's say, classification models or the generative models and whatnot. For instance, if you read the paper by Smart-Aor from 1993, the major innovation they introduced back then was to introduce a so-called transformation aware distance function, and they incorporate that into building a convolutional neural network to do digit recognition. And then what they did was to see what are the kind of transformations that we can apply to a digit without altering its identity, digit identity, and then try to use that small number of the directions in this transformation space in order to define a distance or the geodesic distance over this kind of the same manifold. And there is an extensive discussion by Yasha Benjo in his manuscript in 2009. So let's keep this in our mind because this is going to be the key, let's say, assumption that we're going to rely on in order to do data augmentation without having to design everything ourselves manually. And now we go even further. So let's think about what we actually want to do in machine learning, regardless of whether we do supervised learning, regardless of whether we do unsupervised learning, or even reinforcement learning. At the end of the day, what we really want to minimize is this expected risk. And then this expected risk is defined as a summation over all possible input-output pairs. And then for each and every input-output pair, we're going to weight them according to how likely that pair is. And we compute the loss computed on that pair using our current model, let's say F, parameterized by theta. And what we want is that we want to minimize the whole thing. And then when we look at this, there are two things that we notice. One is, okay, we have to define loss. This is the thing that tells us about the quality of our function. But the more important thing in this case is that we only care about minimizing the loss, so maximizing the quality of our classification or the accuracy on the points that are highly likely under this unknown data distribution. And then this unknown data distribution tells us about the manifold over which most of the realistic data points lie. Unfortunately, we can't really minimize the expected risk directly because, first of all, we don't know what P data is. That'll be great, but we don't know. And even if we know how to evaluate the probability of any given pair, it's often intractable to consider all possible pairs out there. I mean, I was just talking about the image classification, and these days everyone is thinking about the ultra high resolution, high def, let's say, images. In that case, the space of X, the images, is going to be like trillion dimensional. Essentially, it's getting there, not yet. So in reality, what we often do is what we call empirical risk minimization, where we are still going to minimize the sum of the loss functions that tells us about the quality of the classifier, but then we're not going to do that over all possible input output pairs, but only on the pairs that were sampled from this data distribution. And then we often get these samples from the data distribution in the form of the training set. Now, we often have to do the regularization, but I'm going to skip the regularization part because that's let's say, another, let's say, talk. Now, let's try to rewrite it a bit. Oh, no. I was actually trying to, oh yeah, that's fine, okay. So another way to write the empirical risk is to look at, again, as the sum of all possible input output pairs. So we're going to look at everything, but then there is a Dirac delta function that's going to tell us that, okay, we are going to only consider the points that are in fact, that correspond to the training examples. That's the only ones that we're going to consider. But still, we look at the loss function. So you can imagine that this Dirac delta distribution as a proxy to our data distribution that we don't have access to. So if you look here, the point was for us to think about the subspace that corresponds to this manifold, that is the points that have a high probability under P data. But unfortunately, we don't have access to P data. So we're going to only look at the training examples. And then because the number of the training examples that we use tends to be so much smaller than the actual dimensionality or the volume of the space, we almost always get the training examples that were drawn from this distribution that belong to this data manifold, where the manifold is where the P data, the data distribution, had a high probability over. In fact, thinking about that, let's just stick to this my hand-drawn figure. I'm getting like lazy every year, so I tend to just use the iPad and then draw this rather than drawing it much more carefully. If you think about these training examples and then think about this P data distribution, and then if you think about what we just talked about at the very beginning, you notice that many of these small points in the neighborhood of each training data points tends to still lie on this kind of data manifold. It's not like I make small change and then it suddenly becomes, let's say, completely, let's say, off manifold example that doesn't look at all like any training example. So in 2001, Olivier Chappelle, the late Chappelle, and others proposed the idea of the vicinal risk minimization. So if we knew the neighborhood structure, so that is, given any point on the data manifold, if I knew the neighboring structure, that is that what are the neighborhood of these training examples that still is part of this data manifold, then we wouldn't actually minimize the empirical risk. Instead, we're going to minimize what we call vicinal risk. So for each and every data point, or the point in the entire space, now I'm going to look at only the point that belongs to the training set. And then for each one of them, I'm going to look at, again, the entire space. But then I'm going to weigh them according to this local structure. So the local distribution that is centered on the X and Y pair. And then for that, I minimize this loss function. So instead of looking at a single point at a time and then trying to minimize the loss associated with it, for each of the training points, we're going to look at this vicinity and then try to minimize the loss within the entire vicinity. So this P local is going to be what we refer to as the neighborhood structure. And then that is what we can know about, that is via which we know the vicinity of this any given example. And then this local structure is often separated or factorized into two parts. One is the local structure in the input. And then the other one is that if I look at a neighbor in the input space, what should be the corresponding output? Because that one is not really well defined. So then, by looking at this towish, let's say, drawing, you notice that if I had the perfect information about this vicinity, then I can actually approximate this true data distribution much better than simply saying that I only put the probability mass on the point that corresponds to one of the training examples. So this actually gives us a much better, let's say, sense of what the data manifold is, only if we know the local structure.
So I have a question.
Yeah, please.
So thinking about the random noise in the background, image case.
Yes.
So it can be out of distribution, but still it doesn't hurt the class identity. So in that case, is it the vicinity or out?
Yes. So yeah, that's a really good question, right? So what is this vicinity, right? The whole point is to know what the vicinity is, and then in our sense, the vicinity would actually corresponds to any transformation applied to this point that the vicinity is defined on that does not change the identity. Now, what does the identity corresponds to is actually it corresponds to Y. That's the reason in this entire discussion so far, we've always thought about this local structure, not based only on the input, which is often the case with the data augmentation, but it has to be dependent on Y as well, the label. So if we're doing the object recognition, for instance, and then let's say the input image was some image of a cat, and the Y label was cat. Now adding all those Gaussian noise in the background doesn't really change the identity. What that means is that that one is still going to be a pretty highly likely point under this local distribution. So answer is yes, but in that particular context. Yeah, so if you have any questions, please do feel free to ask me those questions, and even over Zoom, on the chat as well. Anyway, all right, let's look at the first part. So what is this P local X prime given X? So we just look at the input. So we're going to just rewrite the local distribution that I wrote in the previous slide, this one into this product of these two parts. Now, there can be actually many other different ways to define it, but this seems like a very natural way to define it. And then there is a good reason why we want to do that. So let's look at the first part. That is the second term, is that is a local data manifold. And then we're going to look at only the input. So what is the input point at the moment? And then what is the distribution that defines the vicinity given that input space? It's often manually designed based on domain knowledge because the X is what the input is, and then we often have a good domain knowledge there. And I'm going to talk about the automatically learning later. But then based on the domain knowledge, we have to design this local data manifold so that whatever is the sample that we draw from this distribution given X is minimally changed form of this X so that the actual identity or the content doesn't change. But at the same time, it still looks like something that is reasonable. So this is an example from the 2009. And you can imagine that if we start from X, there's going to be some digit that corresponds to identity 4. And then there are a number of ways in which we can change, often, let's say, 2 degrees of, let's say, freedom. In the case of the digit, we can rotate or we can shift it a bit. And then this local data manifold would be to withdraw sample from this distribution, and then all those digits are going to look like 4. And also, they're going to look like digit. And if you think about it, if you simplify it further, then if I have enough training examples, and if I have a good local data manifold that is defined based on the domain knowledge, where the domain knowledge corresponds to the transformations that we can apply without changing the identity, then you can imagine that the mixture of this local data manifold local distributions are going to actually tell us about the entire manifold under the true data distribution. Unfortunately, the second part, the first term from the earlier one, is very difficult to define. So what should be the label of newly sampled neighbor in the input space given the input x and its associated y true? What should be this y prime? It's actually almost impossible to design it manually because if we could, it's largely equivalent to just solving the problem directly. Because let's just imagine that I could design it perfectly, almost perfectly. Then all I need to do is, given a new example, I just find the one that is closest in the training set, and then using the training set's label and the training set itself in order to tell what the label should be. So that's actually just solving a problem. So we can't really design it manually. And this is where actually we impose our kind of inductive bias that is not domain specific. And that is the smoothness. So for instance, let's imagine that I'm going to define this P local of y prime as a distribution that's simply going to put the probability mass one, the entire probability mass on a single y that corresponds to the true label of the x. Then it's going to have an effect of smoothing out the target function when we fit it. And then that, you can see it here. Now let's pick any one of the training examples, and then let's imagine a vicinity that is defined. And then we're going to simply say that, okay, all the points in this vicinity shares a single label that is the label of the centered one, the original one. And then by having this kind of, let's say, local distribution that is on the target to be flat, we actually impose the smoothness on the target function that we're going to train. We're going to talk about whether it's a good idea or not later in the talk, but you can kind of imagine that this has to be a reasonably a good idea. Not always, but in real world, feels like that has to be the case because I made a small change that still continues to lie on the data manifold, and there was a small enough change. So the output is probably not going to change too much. It seems like a good idea. So then, putting all these together, what we end up getting is that if we minimize this vicinal risk with a local distribution that takes into account the domain knowledge that tells us about the allowed transformations within the input and the smoothness imposed on the label space, we now can fit, or we can now train a classifier F to be smooth over the data manifold locally. And the reason why we do is because we expect this smoother classifier to generalize better along the data manifold represented by the training set D. And one little detail that I left out here is that assuming that all those test examples are also going to lie on the data manifold. I'm going to get to that a bit later, whether that matters or not, but this is our kind of expectation. And then this is why we want to do the vicinal risk minimization. And then this is what we do when we say we want to do the data augmentation. So of course, unfortunate thing is that almost never we can write the actual distribution with the analytical form in a high dimensional space in particular. So instead, what we need to do is we simply write how to sample from this local distribution. Because at the end of the day, we do the stochastic optimization, and as long as we can sample from it, we can now compute a stochastic approximation to the vicinal risk that we want to minimize. And this is what we also refer to as data augmentation. We start from some input example. We're going to randomly assign some of these transformations that are domain specific in order for us to arrive at a sample that was drawn from this local distribution. So once we do that, the next thing we need to do is we need to sample the corresponding y prime, that is the label that corresponds to x prime. We talked about the usual approach that is simply saying that, okay, let's use the same label from the original x, from which we sample the x prime. But there are many different ways to, not many, a couple of the other ways to go about. One is the idea of co-training from Bloom and Mitchell, 1998. Nowadays, we would call it like hard pseudo labeling or the I don't know, some kind of knowledge distillation, or Another way is to, from 2004 on the what we call entropy minimization, which corresponds roughly to doing a soft pseudo label. But these all are essentially saying that, well, let's train another classifier without data augmentation and using that classifier to tell us about the label for a new example that was sampled from this local distribution.
Question.
Yes.
Yeah, it's very interesting. The foundation of data augmentation. I haven't known much about it. I'm wondering if you're assuming kind of specific application like image classification, because it seems like this Y prime, for example, image segmentation. If you think of a data application, then Y prime can be the class labels for each pixel.
Right.
And then X prime maybe translation augmentation. So in that case, like this Y prime equal to Y doesn't. So in the case of image classification, this assumption works. So I'm wondering the general scope of what you are talking or what you will be talking.
Yeah, that's a great point. So, you know, these usual approaches, especially the first one, seems to be extremely limited because it really says that exactly the output that is associated with the original input X has to be the output of this augmented version X prime. But, you know, that's almost never the case as soon as we move slightly away from these simple classification problems. In the case of structural prediction problem, it's almost always that, you know, the small change in the X should actually make the corresponding small change to Y prime. I'm actually going to talk about it very briefly later, except that I didn't put a slide, so I'll just tell you in words later. But the idea is that these are just some limited ways in which we can set this P local. But if we know more about this rich structure behind the Y space as well, we can use that to make this P local Y prime given X, X prime, and Y also to be rich as well. Yes. I'll get to this. So let's just look at some of the domain-specific data augmentation where we try to exploit the known invariances, equivariances in the target domain. And they tend to be very useful for a few domains that we know: computer vision, speech, all these domains where we have essentially the humanity has studied for the past, let's say, century or so to figure out what are the things that we can do to the image or the speech so that the actual content doesn't change. Unfortunately, this domain-specific data augmentation is not really applicable nor suitable for many other domains. Natural language is one of them. Of course, I'm into biological languages as well, so the biological sequences can be another example. And in that case, what we need is a domain-agnostic data augmentation in order for us to work with a much broader set of domains. But before that, let's take a look at a few domain-specific methods. In fact, one of the most successful use case of the domain augmentation was from the AlexNet by the Krzyzewski et al. 2012, which was kind of, let's say, has been, I think, the biggest success story of modern deep learning so far. And then there, they actually do write about the two different types of the data augmentation algorithms that they used. One was random translation and horizontal reflection. And then the other one is a pixel intensity alteration. I don't think this one is ever useful. But the first one, which is still being used nowadays, is one of the most useful data augmentation or the transformations that we have been using for the computer vision applications. In fact, they stated that without this scheme, their network suffered from substantial overfitting. And then I talked with the authors about this, and then they said it was like substantial, something like almost like a make or break kind of, which makes sense because the number of the parameters they had was substantially greater than the number of training examples they had. So introducing some kind of constraints can only be helpful. Now, this idea has been pushed all the way further nowadays. Nowadays, we really don't care what we apply. We simply define all the transformations that are available in whatever the image transformation library or the image processing library you have, and you simply just randomly apply them in series in order to create all those augmented data. So this is a rand augment. I cannot believe that there has to be a paper about this, but there is still by Kyunghyun et al. And then what they did was, this is like their paper, entire paper. And then what they show is that by doing so, they could improve the accuracy on the image classification as well as a few other problems very, very substantially, which makes sense. although I said that the natural language processing is one domain where domain-specific data augmentation is not really an option, but that doesn't mean that the people haven't tried. So for instance, there is a paper from Wei and Zhou, 2019, where they proposed what they call easy data augmentation. What they did was to randomly select some of the words and then replace those words with the synonyms from the dictionary. Makes sense. Now, of course, that doesn't mean that the whatever the synonym that they replaced makes the sentence well-formed to stay on the data manifold, because often you need to change the words, right? Quite significantly, depending on what kind of language we're talking about. And they introduce random insertion, random swap, random drop. As you can imagine, sometimes they kind of make a sentences that make sense, but often, more often, they actually don't. So not really satisfying, as this kind of, let's say, easy data augmentation kind of, let's say, jumps off the manifold. And our goal is to make sure that our classifier stays relatively smooth over this data manifold. Now, there is a better way to go about that has been used by many of the different people ever since, let's say, 2016, 17. In fact, this idea goes back all the way, but it was revived much better by having a better machine translation systems in their hands, is to do the data augmentation by round trip translation. So I'm going to start with a, let's say, English sentence. I'm going to use a machine translation system to translate it into, let's say, Korean, and then use again the machine translation system to translate it back to English. And often what you end up doing is to generate a bunch of paraphrases. And those paraphrases tend to preserve the meaning, while they tend to have a different, let's say, forms. And then if we choose the pivot language properly, because the pivot language has to be chosen so that it's not way too one-to-one with the original language, but at the same time, it has to be a language for which we have an amazingly good machine translation system, then you can actually use this as data augmentation very well. Unfortunately, not really satisfying because it's supervised and it's very slow. And then choice of the pivot language, as well as all those hyperparameters that are used to produce diverse set of, let's say, examples, more like art than science. So we wanted to do something more. But before I continue, if there's any questions about the domain specifically, because I'm like getting out of the domain specific data augmentation from here, I'm jumping off the data manifold here. All right, so I'm going to start with a bit of an earlier work on Simba. I think self-supervised might be something, but I'll tell you what it stands for. But this is how to use a mask language model, which has become a very much de facto standard in natural language processing for the purpose of data augmentation in natural language processing. This is a joint work with Nathan, who is a PhD student at the University of Toronto, and Marzia, who recently moved to MIT. So what is the kind of basic idea behind the domain agnostic data augmentation? So if you recall from the earlier discussion, it's all about generating sample. But what is all about generating sample? It's all about adding noise. So if we sample from the P of x prime given x, that's actually identical to saying that I'm going to add some noise to x in a way that x prime, after adding noise, stays on the data manifold and is relatively close to the original x. So sometimes we can add some unstructured noise that does not actually depend on x to preserve these properties, like they stay on the manifold, but also make it substantially different. And then this is not the new idea as well. From 1991, there's a paper from Sesfa and Bao talking about how to add this pseudo-Gaussian noise so as to create all those augmented data sets that can be used to make a classifier generalize better. And in fact, if you add small enough noise, let's say Gaussian noise, Chris Bishop in 1996 showed that it's essentially the same as minimizing the trace of the Fisher, I think, or something like, or Jacobian of the neural network. And this is really nice because it doesn't require any domain knowledge. So it's not even domain agnostic, it's a domain-free data augmentation, but it's quite limited because it does assume that the input data lives in a particular type of the space. So we don't want to do that. So instead, what we can think about is that what if we just learn whatever this data manifold is locally? And then we go all the way back to like 2010. And then realize that the Pascal Vincent at University of Montreal already said in 2010, 2009, 2011, and nonstop saying that if we train a denoising autoencoder, the denoising autoencoder is going to learn a local data manifold from which we can let the denoising autoencoder sample. We don't really need to do it ourselves. And then this is the actual figure from Pascal's paper from 2010. And then just looking at this, that's exactly what we wanted to do, right? We already knew what to do there. So we start from, we pick one data point. We're going to corrupt it at some, let's say, unstructured noise. And then we train this neural net, denoising autoencoder, to push it back onto the data manifold. And then now, if my noise was off manifold direction, this denoising autoencoder is going to learn to push it onto the manifold. If it was along the data manifold, it cannot actually push it back because of the ambiguity that is created by another neighboring training point from the same data manifold. So what that means is that by adding all those, let's say, weird noise during training time, this model actually learns what are the off manifold and then what are the on manifold directions. And then once training is done, all we need to do is we add the noise, reconstruct, add the noise, reconstruct, add the noise, reconstruct, and we're going to stay on the data manifold, at least locally. So Pascal already had the idea in 2010. And now let's fast forward like 12 years now, or the 13 years, we are actually training denoising autoencoders every day. It's not, so, I made this particular slice about 3 years ago. So that's why I did, well, everyone is doing an NLP. Now, let's fast forward even further now. Everyone is doing this in computer vision. Everyone is doing this in reinforcement learning. And everyone is really doing it for everything. We're doing it for the protein modeling as well. Yes, protein design, we're doing that. Everyone is doing that. And then that's actually, there's a reason, because it's actually easy to train. It's very, very easy to train denoising autoencoder compared to any other generative models that you can imagine that tries to learn this entire data manifold globally. Now that's a whole new talk, but if you want to know more about it, just talk to me. But yes, we know how to train this denoising autoencoder. That's what we've been doing in NLP for many years, and everyone else in every other domain is doing so. But almost always, so far, even now, most of these masked language models, which are equivalent to denoising autoencoders, are used to initialize a classifiers that are going to be used to solve the downstream tasks. They are often just classification or the regression problems. That's pretty awesome. But what we know is that that's not what we want to do. We want actually this model to tell us whether what are the right changes that we can make to the inputs so that we're going to be able to sample from this local data manifold. Already in 2019, we noticed that that is actually a possibility. So here's an example. So let's say, let me see, what are the things that I know? Okay. Let's say I start with the sometimes virus causes infection. That was the input sentence. And then now, how do I know if this denoising autoencoder or the masked language model know about the local manifold structure? Is that I'm going to perturb it a bit, add some noise, and then I'm going to see if this denoising autoencoder can project it back onto the data manifold that is defined as a set of points where points correspond to well-formed sentences. So I'm going to mask out this infection part. And then I asked the word, or they asked it, I didn't ask it. So Petronio asked the BERT, okay, let's try to push it toward the data manifold and then tell me what are the likely points on the data manifold. And then what BERT returned was disease, cancer, infection, plague, fever, all of which are reasonable, both in terms of semantics, but also in terms of the well-formedness. It's not going to give us, let's say, suddenly my or oh or no or anything like that. In other words, these are the kind of, let's say, qualitative examples that tell us that the BERT or the masked language model samples from this local data manifold. So then the idea is that instead of trying to write down this data augmentation routine ourselves, because with the natural language processing, we don't even know how to do that. Instead, we use the masked language model. So we start with the training set. For each of the example, we apply the corruption, and then we're going to ask this masked language model to reconstruct it. And then the reconstructed example becomes part of this augmented data set. And for this labeling, I'm going to talk about the labeling later, but we can use the self-supervision or just use the same label as it is. And then this augmented data set is going to be combined with a training set in order for us to train a model with more data. And that more data part, actually, it was enabled by this denoising autoencoder, which was in fact trained with a method that has nothing to do with natural language processing. In fact, you can use exactly the same algorithm to train this, what was it, master autoencoder. I was like, what? But anyway, so the Kyunghyun and others work from Facebook from about 2 months ago. You can do exactly the same thing for images, and that's perfectly fine.
So I have a question.
Yeah, please.
As far as I understood, the masking procedure is generated by the BERT, the pre-trained model.
Oh, yeah, so no, masking is arbitrary. So let me just go back quickly. So when we train this denoising autoencoder, there are two important components. One is the corruption process. So given a training example, we're going to add some noise. And then the reconstruction part, that's the denoising autoencoder part. Now, this noise, interesting thing is that the corruption process has to be as unstructured as possible. Something that doesn't know anything about the input domain. And that's the reason is because that's the only way for denoising autoencoder to know what are the changes, what are the corruptions that are going to push the example of the manifold so that it can actually project it back. So in this BERT example, in the BERT example, the corruption process that we apply, well, actually not this one. The corruption process that we use is exactly the one that was used to train this model. That is to pick about 15 to 30% of the tokens from the input, and then about half of them replace with a special token called mask, and then for, I don't know, a quarter of them keep it as they are, and a quarter of them replace it with another word. And then we train a model to reconstruct this masked out or the corrupted version. But in the case of the data augmentation, once the training is done, we just let them reconstruct it, and this is going to be a sample drawn from this local data manifold defined or the learned by this mask language.
My question was, if we can be done, then is it something different from the pre-trained BERT, or
no, it's exactly the same thing.
Then how can we enforce a generalization, because it is exactly from the same thing? So thinking about the rotation or flipping the image classification, that knowledge is quite strong interface bias and something different from the original model. But in this case, we are extracting the information from the same.
Yes.
How is
yes. Oh, so it is possible because we are going to extract it from this pre-trained language model. But then when we do the fine tuning of this pre-trained language model, we're going to use a small number of examples, which means that the model that we train are not necessarily going to stay smooth over the data manifold when we do the fine tuning. So you can imagine that this is one way if we use a BERT as a classifier, but that doesn't have to be the case, by the way. I was going to talk about it. What it does is that essentially we're extracting the information about the data manifold from this BERT, which learned to do so already, so that when we train a classifier, either that be the actual pre-trained BERT that's going to be fine-tuned, or a new classifier trained from scratch, that we continue to impose the smoothness over this data manifold. Because if you start fine-tuning the BERT, who knows what's going to happen?
So fine-tuning knowledge is different from the pre-trained.
Yeah, it's a separate one. So BERT is trained with the unlabeled example, and then we can use whatever the data we have out. So we tested this idea, very straightforward idea, simple idea. And then instead we did some experiments quite extensively. And all those different, let's say, standard, let's say, text benchmark. And unfortunately, I didn't actually write it there. So to your question, we can do the exactly same thing for machine translation as well. There, what we do is that we're going to apply, let's say, BERT, English BERT on the source side, and let's say French BERT on the target side. We actually tried that. That turned out to actually work as well. Not as much as classification has been, because I do believe that the Y has too much noise, but still it was just generalizing slightly better when the target data was really, really small. But anyway, so we compared against the easy data augmentation that we talked about, the unsupervised data augmentation, that is the round trip translation based paraphrasing. And also there was idea from the Wu et al. 2019 that is called conditional bird contextual augmentation. And what we saw, and then we tested all 3 different models. So we did the fine tuning of the pre-trained model from based on which we did the data augmentation. But we also tried on the recurrent neural net as well as the convolutional neural net as well, both of which were trained from scratch. And the results is that okay, so they almost always help. In particular, when we try to check the generalization on the out of domain. But the most important thing along all these methods is that the SIMBA, this particular method that actually tries to augment the data using the idea of the data manifold, this never hurts the baseline accuracy. All the other methods, well, let's choose a better one. All the other methods sometimes helps, sometimes hurts. And then one key property that is shared by all the other methods is that they don't really sample from this data manifold over which all the well-formed sentences lie. On the other hand, SIMBA almost always samples something that is very well-formed, and there are by construction very similar to the input examples. And then what we see is that it really, really never hurts. And in the case of data augmentation, that's really important. The fact that that algorithm doesn't hurt is one of the key properties. But it turned out that it's very difficult to design a data augmentation algorithm that doesn't hurt when we have a very limited knowledge about the actual domain in which the problems are solved. And we did some more analysis. There are much more experiments and results in the paper. You can take a look. But then at this point, some of you might actually realize that, so the whole data augmentation seems to be a bit limiting in some sense. What if we don't want to do the data augmentation in this kind of very, very local? So the data augmentation that we just talked about is that what if P local, this local distribution, is conditioned on an individual example? Is that actually enough? Can we do better? So that is, what if we can do a bit more global augmentation? So we're going to look at not only the individual example, but also we're going to take into account the entire training set that we have, and then try to capture a larger portion of the data manifold as opposed to just looking at a single example and then looking at the small neighbor. In other words, we don't really change too much, but we do the exactly same thing. So we go over every single example in the training set. For each of the training example, we go over the entire space again, but we only look at the points that are in the vicinity of X and Y. But then this vicinity can be significantly expanded by taking into account the entire training set as well, instead of that individual example. And obviously, this is not any new question. Everyone has been asking this question, and then very nice, a bit confusing, but nice to say, method called mix-up was proposed by Zhang et al. In 2017. And then the idea there is that you pick any training example, and then let's say I have an oracle that's going to tell me the perfect path between these 2 examples. And then we now say that any point in this on this path lies on the data manifold. So let's just take a look at the amazing drawing. So let's say I have the 6 examples from roughly the mixture of 2 Gaussian-like thing. I'm going to pick 2 points that are at random. And then there is a path along which any point lies on the data manifold. And then what we want is that for each of the training example, we're going to sample a mixing ratio that tells us where on this path that I want to pick the point from. And then I'm going to sample another example. So let's say I pick this one as the original one. I pick another one. Now I have a path. I'm going to pick the one according to the mixing ratio, and then say that that is going to be a new example that I'm going to augment my training set with. All we need to do is to figure out what is this path and then how we actually sample from that path. It turned out that Zhang et al. Showed that, we don't really have to worry about that path. We just say that it's going to be just a linear interpolation between these 2 points with the interpolation coefficients lambda over the lambda and 1 minus lambda, because it's a convex combination. And even for the output, the target, if it's a classification, they show that, we're going to consider the target as a 1-hot vector. And then we do the linear, again, the convex sum between those two examples. Sounds a bit crazy, right? What? Okay, it doesn't make any sense, but it was working. But if you think about it, wait, hold on. Yeah, if you think about it, it's not too crazy because as long as this kind of linear interpolation exists in the space, you can imagine that it's going to smooth out the classifier along over the collection of all possible segments, these linear segments we get. And then the idea is that as long as this data manifold, however crazy looking that is contained within this collection of all possible, let's say, the n squared, let's say, number of segments, then this classifier is still going to be smooth over that true data manifold as well. And it turned out that they really like the big if, but as long as linear interpolation is defined, it really works really well. And it's not local in a sense that if I pick 2 points, if I pick the, let's say, mixing coefficients with 0.5, it tends to be really far away from either of them. Now, of course, now you can see the pattern. What if the linear interpolation is not defined? Because you're trying to imagine yourself that, well, how am I going to interpolate sentence A with the sentence B? It doesn't exist, right? So this is a slightly more recent work on how to learn to interpolate in order to do the non-local data augmentation in natural language processing. This is a joint work with the Kyunghyun and Seohyung, who are research scientists at Hyundai Motors. I know Hyundai Motors does the NLP. I didn't know either until last year. But anyway, all right. So to think about it, we got to think about the generative learning. So what do we mean by doing unsupervised learning or the generative learning? Concept is super simple. A generative model M is trained on a large set of the unlabeled examples, let's say x1 to xn, where each and every example was sampled independently from the same, let's say, data distribution that we don't have any access to. Once training is done, we should be able to draw a sample from the model and this generative model so that the example looks somewhat like the example from the data distribution. So let's be a bit more specific and say that what we mean by generalization in generative learning is, the first thing is that this sample that x prime that I got from this generative model cannot be one of the training examples, because once that happens, it doesn't generalize. It's not an interesting, let's say, generative model. The second is that this x prime still has to be probable under the unknown data distribution. So whatever I sample has to look realistic, but cannot be exactly like the training example. Because if it turned out to be a training example, then that just tells me that it's overfitting too much. And if you think about it, think about these two, essentially x prime has to be some kind of interpolated version of all these training examples. Let's think about this example that I have drawn again. Red axis corresponds to training examples. And then if I did a generative learning really, really well, what I would get is this kind of learning distribution that puts a high probability on these 3 regions, but it cannot be only on these 3. And then there are going to be some remaining probability masses that are interpolating across these 11 examples. And if I draw a sample from this distribution, because it's really well learned, I'm not going to exactly get this red axis, but these purple axes that are somewhere in a high probability region, but they are somewhat interpolating among these examples. So let's keep this in our mind. What this is actually telling us is that if we view this problem of generative learning as a conditional generative model, we are essentially learning to sample an interpolated version of all these data points x1 to xn. So what do I mean by that? So I start with the training examples. So I have this, let's say, 9 training examples. I have an algorithm, generative learning algorithm A, that takes as input these examples and then gives me back an interpolation distribution. If I sample from this distribution, they are going to be somewhat similar to this, but never same. And then whatever I sample from have to look very realistic. So then the idea is that if I wanted to make a knowledge to the interpolation between 2 points, let's say n, the capital N is 2, what I can imagine is that this algorithm A is going to take as input these 2 points and then give me some distribution that's going to allow me to draw a sample that is some kind of interpolation between x1 and x2. And then of course, we can now tilt this distribution so that the importance of x1 and x2 is controlled by our choice of this interpolation coefficient sample. So we now have a generative learning algorithm A that takes as input 2 data points and the importance of one of them, that is mixing coefficients, and gives me a distribution that actually allows me to sample an interpolated version between x1 and x2. And now we can do meta learning. So we're going to learn this AI group that is going to give us some reasonable interpolated points between those two. So I don't know why I even drew this. This really doesn't tell us too much. But anyway, that's what we want to do. So let's just think about this lambda, this tilting first. So if you think about what this lambda does, is that if the lambda is really high, close to 1, we say that, okay, whatever we draw from this distribution has to look much more similar to x1 than x2. If the other way around, x2 than x1. So what that means is that assume that I have infinite number of examples, but all those training examples are simply the repetitions of either x1 or x2. But the proportion of x1 and x2 in this infinite large training set is defined by this lambda. So out of all those data points that I have, which turned out to be just a repetition of either x1 or x2, a lambda portion comes from x1, 1 minus lambda portion comes from x2. And what do we mean by that? We simply can write the loss function for each of the training examples. There is a pair of the x1 and x2 and this lambda as the convex sum between the low probability of x1 given x1 and x2 and lambda and the low probability x2 given x1 and x2 and lambda. And the weights are given by lambda. Now let's look at this example. Let's say I have all these examples and I pick 2 of these. Now I want to find the interpolation distribution, but with a higher lambda for, let's say, first one. Then I simply say that, well, it has to be higher there, it has to be lower there. And I'm going to simply fit the maximum likelihood destination. And then this is going to the distribution I get. And then once that is done, I just draw a sample. So then, since now we have the per example loss function or the risk score, in fact, this is something that we want to maximize. So the objective function, we can now write the learning objective, like the empirical risk, that is going to be a sum over all possible pairs of x and x prime coming out of the entire training set, so however large that is. And we're going to consider all possible values of lambda between 0 and 1 with some prior distribution that can be some kind of beta distribution with some hyperparameters. And now we're going to maximize. So without the negative sign here, we're going to maximize this expected, let's say, risk there. And we can just do it by the stochastic approximation. We're going to sample a pair, sample lambda, and then compute the risk, and then minimize it. And it's just stochastic gradient descent. Yes.
I'm not sure if I understood correctly. Sounds like, for example, there are 2 modes, and they are separated very far. It seems like, I'm not sure, by controlling the weight of these 2 modes, we can get different distributions,
right?
But I'm not sure if you can make a linear path between these 2 distributions.
Yeah. So that's actually a really great point. Let's actually look at here, this example. So you're right. So if I had, let's say, I don't know, 1,000 times more points from this particular mode, now would that actually make us sample anything that is closer to here, right? Essentially, the question is, now, if there was no constraint that the probability is sum to 1, that's true. But because the probability is sum to 1, there's a natural constraint that says that if I increase this, and generally, and I'm going to talk about regularization. Regularization is going to be key. What's going to happen is that it can go up, but it cannot just go up as a point mass, but it's going to bring up all the nearby places all together. And then when doing so, even if the mass here is small, because this mass is small, greater than all the other places, the path actually gets pulled up with proper regularization. Yes, I'll get to that. That's a great actually cue for the next part. Yes.
So you mentioned it is a meta learning, and
yep.
So is it to enforce the mix-up criteria, or is it enforcing some dependency between the two different examples?
Oh yeah, I did both of which. So you can imagine that which part is the meta learning here is that you can imagine that every time I have x1 and x2 and lambda, I'm going to minimize or I'm going to maximize this objective with a new model, new generative model. And then once the maximization is done, I'm going to draw sample from it. So that will be a usual generative learning. But then the thing is, 2 examples, not enough to tell us about what is the right path between x1 and x2 that corresponds to the data manifold that connects those two. So the meta learning comes from the fact that we actually use all the training examples that are available, unlabeled examples. And then we pick any two, in order to train this model. So what that means is that if we, for instance, pick any 2 of these, now the path that is connecting could vary over this or that. We don't know, right? Because of the unconstrained nature of the problem. But now using all these examples, now what it does is that because I look at these examples, these examples, and then there is a clear path between these two. If I look at all these, so that is the meta learning part.
So
that is
you explicitly enforce the generalization of the pink dots?
Yeah, I'll get to that one. Yes, so regularization is still very key. So I'll tell you about why regularization is needed in the sense that we are not going to tell where the pink dot is because we don't know. That's the whole point. We don't know what they are, but we want to learn to sample those things, right? So we're not going to explicitly regularize not that one, but there are reasons why we need to regularize, and then thereby we actually get this kind of well-formed, let's say, interpolation, even in the case where we have absolutely no idea what are the reasonable, let's say, interpolation. All right. This is a pretty confusing thing, actually. So there were another pair of students who wanted to work on this. And then after about 8 months, they gave up. This idea was buried under the, pile of the papers for about a year. And then only after that it was picked up. So this idea, actually, I wrote down this loss function about 3.5 years ago. And it took us like 3 years to find the people who want to work on it, and blah, blah, but yes, it is very confusing. So let's just show you how we do it, but I'm going to tell you about the regularization. And so what we do is that we're going to make a very straightforward transformer-based encoder-decoder algorithm. But the encoder is going to take us into the 2 sentences, so x1 and x2, and then it gets us all those vectors. And then what we do is that because the number of the vectors is going to differ between the first and the second input, so we use the idea from my own work on the machine translation on the length converter. So we're going to do the up or the down scale. And then the target length is going to be interpolation between the length of the first and the second input. And then it doesn't have to be like this, but let's say we did it. And then we do the linear interpolation in this hidden space. Because we don't know how to do the linear interpolation in the output space or the original input space. So we do it in this hidden space. And then given that one, we're trying to decode out both the x1 and x2. And then we're trying to train the entire thing to maximize this objective function over all possible pairs in the training. And that's what we do. Okay, let's keep this in our mind. But there are a number of degeneracies. What is the major degeneracy? Is that there are only 2 examples, right? So if we do any kind of, let's say, generative modeling on 2 examples, what it's going to do is that it's going to put the probability mass, the entire thing, 1, split between these 2 points, and then 0 everywhere else. And then that's going to be possibly the most meaningless interpolation. So what we need to do is we need to regularize learning so as to address this no interpolation degeneracy. And then there are 3 things I'm going to tell you why those 3 things matter. Okay, masking. Masking matters because if you don't randomly mask out some of the inputs, what it can do is that it really doesn't use any of the contextual information, but it just learns to copy over the words and then reconstruct them. So we need to actually do this kind of masking in order to ensure that this model actually does paraphrasing. Without masking, no paraphrasing. Now, how does it learn to paraphrase? Because it looks at tons of data, not just 2 examples. And the second thing is the Gaussian noise in the hidden representation. The reason why we have to add the Gaussian noise is because in order to do the interpolation, what it means is that there has to be a smoothness constraint imposed on this representation. So we had the Gaussian noise, but then whenever you had Gaussian noise in the neural net's hidden space or any kind of, let's say, unstructured noise like this, you cannot just leave it like that because that's always going to be ignored. This stochastic gradient descent is extremely good at simply making the norm of this representation to be greater than whatever the standard deviation we use for the Gaussian noise, so that it's as if no noise was not there. So whenever you see a paper that says, oh, we had the noise in order to make it regularize, generalize better, it's all bullshit, right? It's all bullshit. You should know. That's why you need a third one, is that you need to constrain the norm. So we decay the all the hidden weights, hidden representation towards zero, so that the norm is going to be constrained. So we had these three of them. Then what happens is, okay, random masking allows you to do the paraphrasing. And Gaussian and the decay towards zero is going to actually allow us to ensure that every point between any 2 points in the hidden representation space is going to be completely filled up. So we're trying to fill up the space so that the interpolation makes sense. Now, but then you have that says that, okay, so we're going to do some kind of interpolation, right? It's not going to be either x1 or x2 that we sample out, but you have to do something else. But how do we know that it's meaningful interpolation? I'm going to give you a very unsatisfactory answer. Is that it actually arises from our use of deep neural networks. I mean, I'm not supposed to say this, but this is exactly what happens. And then if you have seen these recent, let's say, demos of, let's say, path-aware language model from Google, or Chinchilla, or the GPT-3, or all those things, if you were ever surprised by how good the generated text were, and I was generally, right, genuinely, then we know that these language models know how to interpolate between all this amazing amount of text in a way that is always well-formed, and thereby on the data manifold. If that is the case, if we believe it, then we have to also agree that this approach, when trained on a large amount of data using the exactly same parameterization, will be able to interpolate it. But only thing that changes is that we always condition the entire generation procedure to be on these two examples, so that the interpolation, the whole distribution is going to be skewed significantly to focus on these two examples with the ratio that is determined by lambda. Not the most satisfying answer, but if you think about it, and if you are surprised by any one example from GPT-3, then you have to trust me that that's going to happen. So we're going to rely on Ilya Sutskever to convince you that it's going to be a more meaningful interpolation. So does it actually learn to interpolate? So the answer is yes, but these are boring. Plus, I'm going to show you some good examples and some horrible examples. So these are some good examples. We trained this model on the Wikipedia. So we start with the pre-trained BART, and then we fine-tuned it as this learning to interpolate on the Wikipedia, and then we're testing on the movie reviews. And let's look at the first, and then we're doing some extreme interpolation, like in the middle kind of thing, right? So there was a question earlier. And then what we see is that the first input makes sense. The first one was relaxing his perfect quiet place and proud in his message. Second one, the plot is both contrived and cliched. And then Linda, when we sample from it, well, we did a beam search. The plot is both perfect and cliched in its message, but it's good but not perfect. It's just not enough paraphrasing. But let's look at the second example. Richly entertaining and suggestive of any number of metaphorical readings. The second one is the film is superficial and will probably be of interest primarily to its target audience. Now, the interpolation that we sample from with a 0.6, which is pretty extreme still, the film is very entertaining and will probably be of interest to many of its target audience, regardless of its genre. So this kind of any number of metaphorical readings, kind of paraphrasing to regardless of genre and so on. So we do see that some of these are the kind of meaningful interpolation that we see, even with a very extreme interpolation coefficients. And there are some interesting examples where where we see that our lack of kind of knowledge about the domain or what interpolation means in natural language is interpreted by this learning to interpolate Linda in a way that we didn't expect. So here, the first input is about the idea how awesome the menu was, and then how the drink was great. And then second one was like, oh, how horrible the place was. But what you notice is that when we generate from it, it actually has much more content from the first input, but then how it's written down, how you write it down. So the syntactic information is so much closer to the second input. So what it does is that in this particular case, the Linda kind of takes the semantics out of the first input and then syntax out of the second input and then mix them in order to build an interpolated example. And in some sense, this was not what we anticipated, but this is what can be considered as an interpolation because we never actually said that, okay, it has to be some content that needs to mix or the form that needs to mix or anything like that. But this is what was learned based on this training. And of course, there is a bad example as well. And then unfortunate thing is that just like any language generation models that we have seen so far, it does hallucinate, especially when the original sentences are out of the training domain so far away, or they are not well formed, as in like the Wikipedia text or something like that. So here, I think the first one is engaging imaginative filmmaking, and it's nearly 2.5, and then that's it. The film has this moment, but that's it. And then somehow we start with, okay, it has to be something about the film, but it's going to just make up the stuff. Although, it kind of makes sense, that's probably how it happens in general. And we can now use Linda in place of the linear interpolation in the case of natural language processing, just like using it with the mix-up. Now, unfortunately, there aren't many comparison points for this kind of global augmentation in natural language processing. So we compare with the usual EDA, Simba, so our own work, as well as the reason, let's say, naive way of applying mix-up. Simply saying that, well, length differs, we're going to just add some kind of, let's say, padding tokens. And then all those tokens, we're going to just do some kind of mix-up. And then what we see again here is that the Linda is the one method that kind of, let's say, never fails over the baseline. And then again, with the data augmentation, you almost always fail against the baseline. So we ran all these experiments. They are all in the paper. But the thing that I want to talk about is that yes, we should definitely do this kind of global data augmentation that tends to work better in general when it comes to generalization. But the global data augmentation is really difficult because we don't know how to do that almost always. But if we learn to do it, there seems to be a way for us to use our advances in generative modeling as well as meta learning in order to do it better. Now, do I have some time? I have the third part, which some might actually find more interesting as well. All right, I'll go through it really, really quickly because I was expecting to being asked this question actually. So, this is the thing that I actually said earlier. So we expect this smoother classifier to smoother over the data manifold to generalize better. That was the whole premise. And then empirically, yes, the answer is yes. We could see that on a bunch of data sets. But then, is it really true? So there was two indirect. Can we get a more direct evidence that the smoother classifier over the data manifold will indeed generalize better? So we thought, well, we should have asked the question in 2017, but well, let's answer it even ask the question now and then try to answer it, even though it's late. So then we're going to turn this vicinal risk that we talked about into a smoothness measure. So in the vicinal risk, the idea was that we go through all the training points, and for each of the training points, we look at the local neighborhood, and then we say that okay, in the no local neighborhood, the loss has to be low, while the target class doesn't change too much. So it has to be smooth in the local vicinity. And then we do that for all the training examples. Now, how can we turn it into a smoothness measure? What we're going to do is we're going to look at, let me see. Okay, so we're going to look at all the target domains examples. So we're going to say somebody gave us a set of examples, and then we're going to look at all of them. But then for each one of them, we look at the local neighborhood as well. And then within that one, we say that, okay, our classifier's prediction has to be similar to the original targets. Or at least it says that between 2 points in this vicinity, each vicinity has to be close to each other. I think I can write this one so much better. But anyway, okay. The idea is that I'm going to look at all the vicinities given a target set. And then within each vicinity, the predicted labels has to be similar to each other. That's going to be a smoothness measure that is motivated, in fact, directly transformed from the vicinal risk that we talked about. And then this is now instead of training a classifier given the training set, but we're now given a classifier and the target distribution, and then this actually tells us how smooth this classifier is in the under the target distribution. This is too horrible that I'm going to just pass, but anyway, so this is much better. So what we are saying is that let's say I pick one point, and then I'm going to look at the vicinity, and then I have a classifier. I'm going to look at, given any pair of the points in this vicinity, do they agree with each other, the labels? So then when we say that this is less smooth, while this one is much more smooth than the other. So this is what this smoothness measure is going to compute. And to implement the whole thing, we say that, well, target is given. This one we need to know. This one we're going to learn that local data manifold. And then the target is going to be what our classifier tells me, and then what the local target is going to be the same thing. And then if they are same, then we say, okay, same. All right, so smooth enough. So just looking at graphically saying, we're going to pick one test example from the test set. And we sample from this neighborhood. We're going to sample a bunch of them from the local neighborhood using, let's say, mask language model or whatever we want. And then we're going to look at the agreement rate according to this classifier. And then any classifier, given any pair of classifiers, we say that the classifier that is smoother, so it has a higher agreement rate, is going to generalize better. So we don't really use a label example, right? We're going to see if we can actually guess which one generalizes better based on this smoothness. Because if that is not the case, we're kind of doomed. The whole, let's say, research program of the learned data augmentation kind of, let's say, breaks down totally. And somehow no one has actually checked it yet until now. Evaluation is actually pretty tricky because essentially we're computing the correlation between the local data, local manifold smoothness and generalization. To do so, we need to have a lot of well-trained classifiers. They are well-trained, but have a high degree of diversity in terms of the accuracies, because we want the ones that generalize worse than the others. But they have to be trained well. They have to be trained well because you can always make a worse classifier that has amazing smoothness by simply not training. If you set the weights to be all 0, perfect smoothness, but that's useless. So we need all the well-trained classifier that was trained to minimize the expected risk as well as we can. And among them, we want to look at the smoothness and then trying to correlate the smoothness value and the generalization accuracy. So for different data sets, the sentiment analysis, natural language inference, and so on. And then I told LS students earlier that they hate sentiment analysis, but we tend to use it because there's a kind of curse that natural language processing people have. But we try the convolutional data, Roberta, and then we use various hyperparameters in order to create, let's say, more than thousands of the classifiers in order to check this correlation. And the point, and one thing is that we want to know whether the data manifold matters, right? Local data manifold, does it matter? What if it doesn't matter? What if just a random, let's say, perturbation is fine? So we tried all this, and then we also used some of the latest, let's say, manifold agnostic baselines, ATC, average threshold pump. It turned out, let's look at the classification sentiment analysis, and this is the linear correlation coefficients we have. It's super high, it's 0.7. 0.7. This one actually almost won with the Roberta. What this actually tells us is, but then what that happens is that that happens often when we use a good, let's say, manifold that has been learned from the data. And then what this tells me is that with extremely high chance, I can tell which classifier is going to generalize better without knowing the actual labels associated with the target set. And then this actually even happens when we are looking at the extreme out of domains, where we use now the drug reviews from the drugs.com. They don't look at all like the movie reviews or the product reviews from the Amazon. But what we see is that we get very high, let's say, correlation between the generalization accuracy and the smoothness metric. And then we could actually see the similar observation on natural language inference, as well as the other, when also using other correlations. And the paper, the more experiments and results are in the paper, but the paper is not online. Just throw me an email, I'll send you the paper. I definitely should download it online. And we did some more analysis as well. And then what we see is that the number of the samples we get from the local data manifold doesn't matter too much as long as we get few, let's say, 5 to 10 of them. Although we question whether this is about this algorithm itself or whether it's about the problem being too simple. I can't really tell. But the one nice thing is that all we needed was to get about 1,000 examples unlabeled, right? So we're not using the label. 1,000 examples to tell which classifiers are going to generalize better, which is makes it really practical to use, and also confirm that the whole, let's say, research program on data augmentation has not been a moot point. So that's actually great. But anyway, okay. Blah 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 blah. But okay, the final slides. Now, unfortunately, there are way too many remaining questions left unanswered. So the one is that, okay, most of the experiments here I presented were done with the natural language, but how general are these observations and conclusions beyond natural language processing? In fact, one of the PhD students said, and you tried it on the computer vision for the, let me see, checking the generalization, it works pretty well. It works actually as well. So I wouldn't be surprised if all these observations apply also to computer vision as well as speech. Second thing is that this is one kind of a big question is that, okay, so it turned out that they're doing unsupervised learning as a denoising order encoder. It certainly captures data manifold. How does that actually connect to their super effectiveness as a parameter initializer? Are these two kind of equivalent with each other? Maybe, maybe not. There are some the hand wavy ways to say that, well, they are they're essentially equivalent, but there are also many other ways in which they don't have to be equivalent. So that's the question. The final thing is that is more of a future direction is if the qualities of the samples from this data manifold looks really high, and then it can actually tell us about the generalization in the out of domain example target set as well. Can we then use it as part of the kind of active learning, but to make it even more active by saying that well, we don't wait for the stream of data to come in and then ask oracles for the labels, but we're going to say that well, what if we propose the data points to be labeled by the oracle actively in a series in order to maximize the maximize the sample efficiency in the active learning scenario, such as, of course, drug discovery and whatnot. And that actually concludes my talk. Thank you very much for your attention, and I'm open to questions. Yes.
There are 2 questions in the chat.
Okay. Yeah, chat. Yes, I think I can see it here as well. Let's see. There is a question from someone. Can we guarantee that the target variable interpolation will work same as input interpolation? If not, how can we? Oh, yes. Okay. This is a great question. Let me just go back to the, oops. Let me just try it again. Let me go to the, so the question is whether in this kind of mix-sum scheme, what everyone has been doing is to use the same interpolation scheme for the input and output spaces. So in this case, it's just a linear interpolation, but there is absolutely no reason it's going to be the optimal thing to do, because all we need is some kind of interpolation that are going to correspond with each other. So in the case of Linda, the learned interpolation scheme that I talked about, obviously it's not linear interpolation. So what is the right interpolation scheme to use in the target site matters. In our case, it turned out that just fixing it to the one of those with the lambda. So just doing the linear interpolation was fine. But what that actually tells us is that if we already use the 2 different interpolation scheme for the input and output, and then it gets much more complicated if the output is also structured, like the machine translation or the object segmentation. Then we can actually train 2 different unsupervised learners that's going to propose the different ways to interpolate them. But that seems to be a lot of work as well as a lot of, let's say, uncertainty on the way. So there's going to be a future direction to be investigated. And the second question is from Luis. I have a general question. What are the main advances in the last few years and the main challenges in data augmentation applied to sequence-based drug discovery, protein design, antibody design? Okay, yes. Yeah, a lot of challenges in terms of the data augmentation. So in fact, all the things that I told you actually corresponds to data augmentation in protein design. And so let's say protein design or the antibody therapeutics design. So there are two things that needs to be done. One is that we need to be able to propose a candidate designs that are at the edge of what we know, because how we do the exploration. Now, for doing so, that actually corresponds exactly to the data augmentation that we talked about. What does data augmentation do is that given all those training examples, now we need to propose the, let's say, perturbed examples that are right at the edge of what we don't care and then what we do care. So we actually do use denoising autoencoder in order to propose all these, let's say, candidates, and they do okay, but they are not doing as well as we want to. And then second thing is, let's say we got tons of candidates coming out of this generative model. Second thing is to test them, because we need to know which ones are actually good. Now, ultimately, real biology does not live in the computer, so we have to work with the lab in order to synthesize them and test them in various setups. Now, before that, which costs, I don't know, $500,000 every time we run the experiments, and then we're burning like tons of money at the moment. Before that, what we actually need to do is to ensure that we know what we are sending to the lab. And then to do that, we need to build a lot of computational oracles or classifiers that are going to tell us about the various properties so that we can choose ones that we want to send with the high confidence as well as the high level of the expected information gain. Training these classifiers is very challenging because the number of examples is really, really small. And one of the reasons why we do data augmentation is in order to utilize all the data we have, but where we have only a small number of label data. So in fact, at the moment for the drug discovery, all these data augmentation algorithms are here to be applied, haven't been applied that extensively. I think that's actually it for the questions from Zoom at least.
Sorry for
Yeah, please.
So in the first paper, Simba,
Yes.
I think the paper is related to the GFlow and MCMC.
Ah,
So
yeah.
because it is going back a few steps and going forward a few steps again. So
Yeah.
how do you think about?
Yeah, so I mean, Simba is way before GFlowNet, so yeah, not related, but but the whole idea of, let's say, GFlowNet or any kind of, let's say, generative modeling, is that we need to be able to essentially ensure that wherever we start in the input space, I need to be able to map that point to the point on the data manifold that is at the highly likely point. Now, it doesn't have to be the same space. Then now you can lift this whole space into another space and then say that whatever the point I get from this point, if I project it into the original input space, that point has to be highly likely, right? Now, if you start from there, then what is the natural way to build this whole system is that I'm going to start from this input space, wherever I am, and I'm going to move it to this lifted space so that the marginally is very simple prior distribution that I know how to sample from. And then from there, I need to be able to go back to the highly probable space that is right next to it. Now, in the case of denoising autoencoder, what we do is that the space is shared with input space. So the corruption is how we move off the manifold, and then that part is easy to sample from and then go back. And then GFlowNet does exactly the same thing, but in the multi-steps, and then Simba does the same thing. But what that means is that we can use GFlowNet or others to do a similar thing. But there is one major disadvantage, or actually two major disadvantages of those global generative models. Is one that we often want the smoothness to be defined in the locally, but the global models does not necessarily give us this kind of local neighborhood idea. And the second thing is that I don't think we can train these large-scale global generative models. I think there is a fundamental issue there. Is that the issue is that okay, so to train this generative model, we have to ensure that the probabilities are high on the data manifold that is low dimensional. So that seems easy, but the flip side is that we have to ensure that the probabilities are low on the off-diagonal space, off manifold space, which is by definition, because we said that the manifold is low dimensional, is high dimensional. I don't think we can do that. I feel like we're losing, that's a losing battle that, like the Sungjin knows, Sungjin spent some time on, I also spent some time on long ago, and I think that was a losing battle. That's why Sungjin is not working on that anymore. I'm not working on that anymore. Yes.
Yeah.
Yes. Yeah.
Yeah, this is kind of maybe general question. So because you mentioned a little bit about out of distribution generalization at the end. So to do that, I think the correct or principled way is to learn some kind of causal structure in general, but I don't know how NLP people think about it. Like, should we learn some kind of causal graph, latent causal graph, or another aspect is like just GPT-like big models. Some may believe that by providing a lot of data, maybe even causal structure can emerge within that big network. So I'm wondering your opinion about causal representation and
that's a great question. So I'll just quickly answer the first part for a second, because so the one thing that I tried to make clear is that here, when I say OOD, it's actually not out of distribution, but it's out of domain. So the major difference, and then the reason why this major difference in our case is that so this is domain, because we're not talking about the distribution, but we're saying that someone actually gave us a set of data points, and then we are simply assuming that regardless of which kind of data sets, input data sets we were considering, right? The whole process of classification is shared between them. And then we use the unsupervised learner that uses vast amount of unlabeled data that's going to cover both of these domains. That's the reason why this neighborhood structure makes sense, so that the smoothness makes sense. So in that sense, this one does not actually require us to actually capture the causal relationship between the input and the output variables in order to the out of domain or the out of distribution generalization. Because in this case, as long as that structure is shared, even if we misspecify them, as long as we misspecify them in the same way, doesn't really matter, right? But when it comes to causal, let's say machine learning, my view is that because I'm not entirely sure whether this kind of, let's say, purely data-driven approach can actually help causal inference, except for the case where the causal inference or the causal structure discovery is so computationally demanding, so that if we want to do a bit of an amortization of the cost into the training cost, so as to speed it up, I don't think that purely data-driven approach can actually help us too much. But then another direction that I've been pursuing recently has been telling me that but it turned out that a lot of the things that we know about the causal inference actually can tell us or gives us a justification why some of the, let's say, the concepts in machine learning, such as multitask learning or the multimodal learning, have been successful in certain cases. So there is one paper that I put it on arXiv, and then that is on analyzing multitask learning. And there, what we did was that, if we assume a certain, let's say, causal structure of the problem in a multitask learner, then in the particular case, multitask learning is guaranteed to help. On the other hand, the existing concept of, for instance, multitask learning, we always just say, because of representation, it has to be good, but we don't really know when it should be helpful, when it should be hurtful. So causal inference seems to be the direction going from causal inference to machine learning in terms of helping each other seems to be easier to approach, at least from my perspective. Yes.
Thank you.
There is a question in the chat.
Yes. Stephen.
And if anyone else has questions, we'll try to wrap up in a few minutes.
There's a question by Stephen about another extension question, but would these techniques also work well for regression tasks? I think so. But the issue with the difficult part of the regression task is that it's very difficult to define a loss function and also the parameterization. So as long as we can define a very sensible loss function with a sensible parameterization, I don't think there is any reason why what I presented today wouldn't apply. Yeah.
Okay. Go ahead.
So there are many work going on to actually to quantify some value of each data sample, and based on such work, people can even prune like 50% of the data and can still achieve the similar generalization ability. And I'm just wondering, can other works also just focus on some value of data, which is good for generalization? So I'm wondering whether you can imagine kind of combining such kind of different view of data augmentation, the pruning data validation.
Right. So the data pruning versus, let's say, data augmentation. Data pruning is a bit weird thing, right? So you can always think about it from so because we write papers nonstop, I mean, there's a whole community, right? So what that means is that we can easily be confused by whether, by the things that we know about the problem because of all these papers, or the things that are actually true from the beginning. And then what that means is that some people can easily say that, well, this data or these problems are so, let's say, constrained or the simple, so that we probably don't need, let's say, million examples, right? But then the question is, how do we know that we don't need a million examples? Is because we have already trained model with a million examples multiple times. Because to know so given any data set and then any data point, in order to know the importance of this example, the only way we know how to do it is actually to train a model without this example and then compare it against the model that was trained with this example. And what that means is that without that, we cannot really be certain about the importance of that, because the importance or the complexity of the problem is essentially to compute the mutual information between the label and the input. And then if that information is really high, then it means that, well, we don't really need much of the example. We just need to look at the X and the Y is going to come out, automatically and all those things. But then we don't know how to estimate those quantities anymore. Only way we know how to do it is to train these neural nets. It's going to be a bit controversial, I know, but that is the best way we know how to check the compression rate of everything and everything. So in that sense, image pruning, I feel like, the data pruning, I feel like that is more of a kind of, say, the post-hoc approach that we can use in order to, let's say, speed up the subsequent training or the deployment of the systems. But I don't think there is a way to do the kind of prospective, let's say, efficiency gain or anything. Now, there is an aspect of the meta learning that changes a lot, because many of the data sets or the problems tend to be similar with each other. And maybe if we know some of the data can be pruned, maybe we can predict for a new data set that how much pruning we can do. But that's kind of, let's say, the meta level. So, but before that, in principle, I don't think pruning is a thing that we can do prospectively. It's always retroactive for the retrospective.
There is one more question.
Okay.
Then we're kind of.
Yeah, Chongguan asked the question. Let me see. GPT-3's generation has lots of issues like hallucination, not factual, and sometimes awkward. How can we trust augmented data? Is there some work for that, the well-refined data would be needed? Or prompt engineering, do you have any opinions of GPT-3? Yeah, so the GPT, so yeah, so many things to talk about. But anyway, okay. So indeed, all these language models that we use for data augmentation do not give us a perfect examples. In fact, they are not even going to preserve the semantics generally as we want them to. But then for the purpose of data augmentation for training a classifier, it's actually less of an issue. Because as long as our data augmentation is sufficiently concentrated and still largely contain the data manifold, it just makes the classifier smooth over the data manifold. So in that case, for this purpose, it's actually perfectly fine. But indeed, these language models do generate things that are not desirable, and then we need to do something about it. And I think the first step for us to do it is to, as scientists and engineers in this particular field, I think that we tend to be excited way too easily. I think our job is like be half excited and half critical, but at the moment, I think that 90% excitement and the 10% criticism. So I think that we can start from there. So yeah, definitely a lot of issues with the language generation models. And that's the reason why we are here.
Yeah, and that's why we'll keep our jobs for the next.
That's true as well. Yes, to make people skeptical. Yes.
So it's been a very long time since I hosted an offline talk, and I just realized that I didn't say all these wonderful things about Kyunghyun before we started, but I think it's pretty obvious, and it's now that the talk is done, I think it's even more obvious that his insights and his talk is just wonderful. So let's give him another round of applause. We'll have the video available also, so after the talk, and we're off to dinner.
Thank you. Thanks for attending.